Yeah.
Okay, so we're going to run through the derivative review. What do you guys want to see?
All of it.
All of it. Okay, so I'm not going to do this one. You can look up the old ones. The differentiability?
Yeah.
I just need to know what, like how.
Yo, x squared minus 16 without absolute value looks like this. Okay? Where it hits at -4 and 4. So absolute value looks like this. Creating corners at -4 and 4. So you would say, not differentiable. Y'all can do this. At x equals 4 and x equals -4 because there are corners, okay? Great, are corners, great. Boom. Okay? Now, if you know what the graph looks like for 3, just derive it and see where the derivative is undefined. Oh, good. dy dx equals 4 over 5x to the 1/5. That's not differentiable. Cool. Or that's not defined. The derivative isn't defined when the denominator is 0, which means what x value? 0, that's right. So not differentiable, whatever, at 0, differentiable at x equals 0, since dy dx is undefined. Simple enough? Cool, and just do another one for fun. If you had something like this, y equals x over x squared minus, doesn't matter, 25. Not even deriving that, where's this function not defined? 5 and -5, so you'd write not differentiable. You can derive it if you want, but you're going to find the same denominator. So you're going to write not differentiable at 5 and -5 because either y is not continuous, or y is not defined, or y prime is not defined. Does that make sense?
But do we have to write all three?
No. Any one of those is fine. Any one of those is reason enough for it not to be differentiable. Okay. Let's keep going.
Okay.
Differentiability. We just did this on the board. Do we have to do this?
Yeah, because we did step by it step.
Oh.
for a long time.
Okay. Yeah, this shouldn't take crazy long. If you want to make a piecewise function differentiable, you got to make sure the pieces meet at each of the splits. Now this function only has one split, -1. So when you plug in -1 for x, the sides, they have to meet each other. So if you plug in -1 for x, this becomes -2a minus 5b minus 1. That has to be the same as when you plug -1 into the bottom, which is -b plus 3a minus 2. Can we handle that? Okay. Now, so that being true right there, that equation makes this thing continuous. And I'm just going to clean it up a little bit, get all my variables together. So we can add 2a. It doesn't really matter which way you do it here, but I'm going to add 2 to both sides, which makes this a 1. I'm going to add 2a and 5b to both sides. So you get 4b plus 5a. Right? If I'm making a mistake, let me know, because I'm recording this. I want people to see. Okay. All right. We also need the derivative to meet each other at -1. So we derive it. And the derivative of this thing is 6ax squared. Stop me if you have any trouble with this. Unless you're watching at home, then just listen to my amazing voice. 6ax squared plus 5b. And then the derivative of the bottom is just b. Okay? Because we're deriving x. A and b are numbers. So we need those two things. Technically, there's like an x less than -1 here. It doesn't really matter for our purposes. Okay? Oh, it doesn't matter which one the equal sign on. No, whatever. Okay. We need them to be equal when x is -1. So you plug in -1 and you get 6a plus 5b has to equal b. Okay? And the whole trick here is now we have two equations. We have this equation, which came from making the functions meet each other, and we have this equation, which comes from having the derivatives meet each other. Okay? You got to pick one of them, whichever one looks simplest, solve for one of the variables. The second one to me looks easier, so I'm going to subtract 5b. That's going to give me -4b. I'm going to divide by -4. And that gives me -3 halves a is b. This will be the same thing every single time. Okay? Plug in the x value, set them equal, derive, plug in the x value, set those equal, choose one of those equations to solve for one of the variables, sub it into the other equation after you simplify it. So I know b is -3 halves a, so that means this becomes 4 times -3 halves a plus 5a. And 4 times -3 halves is -6a. Cool. So this is -6a plus 5a. So I'm running out of room here, right over here. But you basically get this. 1 equals -6a plus 5a, which means 1 equals negative a, which means a has to be negative 1. And once you know a is negative 1, you come all the way over to here, and you know that b then has to be negative 3/2 times negative 1. So our answer is right there. Easy enough? Every one of these will be the same. What's up? Cool. And let's run through some of these derivatives here too. We could probably crank these out in 15 minutes. Oh man, we could probably finish the whole thing in 15 minutes. Look at all this. Yeah, we're going to go hyperspeed. Superhuman speed. Ready?
Wait, so is this just the answer? A?
Yeah, the question is find a and b, so it's differentiable. That's the answer right there. And when b is 3/2 and a is negative 1, that thing will be differentiable. Okay? Because the pieces will meet and they meet with the same slope. All right, so here. Remember, we're really deriving both sides of this equation, but once you have y equals something, when you derive y, you just get y prime or dy dx. Okay? I'm going to write y prime. We have to do the product rule here. Product rule says derive the first thing, which is ln of x squared plus 1. That is 1 over x squared plus 1 times the derivative of the inside, which is 2x, and you multiply that by cotan x plus. Okay? Leave the first thing, ln of x squared plus 1. Derive the second. Derivative of cotangent is negative cosecant squared x. Okay? Okay. Number 6. Yeah. Cool. Number 6 is quotient rule with a product rule in the numerator. So, dy dx, or y prime, same thing, is equal to, leave the bottom, low d high, right? So secant of x times, I'm going to put the derivative of the numerator in brackets just because it's going to be a little big. Okay? The derivative, so we got to do product rule, which says derive the first thing, which is 2 to the x. So ln of 2 times 2 to the x times the second thing. Right with me still? Plus, now we derive the second piece of that thing, which is root x. And the derivative of root x is 1 over 2 root x. And you multiply that by 2 to the x power. Cool. Minus, now we have the numerator, which is 2 to the x times root x, times the derivative of the denominator, secant x tangent x. Let's squeeze that in there. And that's that whole thing. And you remember, so this some kids keep forgetting. You got to divide that entire dumb thing by the denominator squared. Okay? No. So listen, we're not deriving secant squared. It just is secant squared of x. Like, yeah, some things are just what they are. You don't have to derive everything you see. You're not like a deriving machine, like bah, bah, bah. Right? Like secant squared goes down the bottom. Don't derive that. Yeah, definitely. Okay? But look, we're just going to leave it like that for right now, okay? Right there. Yeah.
If it was just secant squared of x, how would you derive that?
If you had to derive secant squared of x, let's make sure we don't have one of those somewhere else along here. Okay, if you had to derive a secant squared of x, so let's say this was y. Cool? When you derive that, you get y prime. Bring down, anytime you derive anything squared, you get 2 times that thing to the first power. That's just x squared, right? 2x. Then you multiply that by the derivative of the inside thing by chain rule. And you could put those secants together. It's really this, yeah.
Wait, so technically the squared is the f of x?
Yes, yeah, squared is the outside function. Okay?
So even though it's like right next to this, it's still f.
It's not right next. Secant is inside of squared. Secant's being squared. Okay? That's why we're driving squared first. It's the outside function. Okay, let's go back over here. Arc cosine of something inside of it, the derivative of that is negative 1 over the square root of 1 minus the inside thing squared. So we're squaring that whole log there. Is that okay? That's always the derivative of arc sine. Then you multiply that by the derivative of the inside thing, and the derivative of log of 2x, log base 2 of x, is 1 over ln 2 x. Okay? That's it. Number 8, the derivative of an arctangent is always 1 over 1 plus the inside thing squared, and e to the x squared is just e to the 2x. And then you multiply that by the derivative of the inside, which is e to the x. You can either put it on top or just tack it on the end here. Okay? Number 9, the derivative of cotangent is negative cosecant squared, and the inside thing stays the same. But then you multiply that by, yeah, that's x to the 1/6, right? So you get 1/6 x to the negative 5/6, but just put it down in that denominator while we're doing it. There you go. Not too bad, right? Okay? Let's keep going. Number 10. Now we have y built into this stupid thing. So we're just going to drive both sides, okay? Don't make that face. This is going to be fun. Ready? The derivative of 3x cubed, this is easy, is really 9x squared. And we're technically multiplying that by a 1, because that's the derivative of x, okay? So I'm not going to write that, but there's a times a 1 there. Plus 20y to the 4th times the derivative of what was being raised to the 4th. And that equals the derivative of e to a power is always e to the same thing times the derivative of that thing. Cool? And now, because I can do this digitally, I'm going to move this thing here, because it's got a dy dx, over to this side. But when I do that, it's going to be a minus. Okay? And that puts the 9x squared right here. You can handle that?
Do you have to isolate that?
We have to get all the dy dx's on one side.
Do you have to divide by e to...
Well, I'm going to factor out dy dx now. Cool. And that's going to leave me with 9x squared equals e to the y minus 20y to the 4th. And that's going to be times dy dx. And because I want to know what dy over dx is, I'm going to divide. I'm going to write dy over dx on this side, but I'm going to divide both sides by those parentheses.
E is e to the 2y, right?
Okay.
Would the derivative of that be 2 times e to the y?
Yeah. So let's check out this hypothetical here. If we were deriving e to the 2y, let's say x equals e to the 2y for some reason, this side becomes a 1. The derivative of e to a power is always e to the same thing times the derivative of that thing, and the derivative of 2y is 2 dy dx. Okay? If this was 2 times the square root of y for some reason, then the derivative would be e to the 2 square root y times deriving 2 root y is a half times 2 cancels. Is that okay? If the 2 is there, you're going to multiply by a half. You're going to get y to the negative a half. Then you multiply that by dy dx. It'd be 1 over root y times dy dx. Yeah, the 2's cancel. But for right now, really, you can leave it like that. It's fine. I don't care. Okay? Let's go back over here. Everybody good on this one? Okay. So, 11, similarly, is implicit differentiation. So we're going to derive this thing. The first part here is product rule. This part here is just arcsecant rule. And this is ln with a product inside of it, which this is going to be a mess. Okay. So, we're going to derive that first thing as a product. You derive x, you get 1 times root y. Plus, leave x. The derivative of root y is 1 over 2 root y times the derivative of the inside. Minus. The derivative of arcsecant is 1 over the absolute value of the inside times the square root of the inside squared minus 1. Everybody okay with that? So this piece right here is the question. It came from the fact that when I derive this, I'm leaving the x, I'm deriving root y. And the derivative of any square root is 1 over 2 root that thing. Okay? So, we derived the arcsecant, but we didn't derive what's inside. So at the end, we have to multiply by the derivative of y with respect to x. Is that okay? I'm going to zoom out a little so we can fit this all on one screen. That's going to equal ln, the derivative of that is always 1 over what's inside times the derivative of the inside, which we have to do product rule with again. So you derive x, that's 1 times y, plus leave x, derive y. Okay? And now we're going to get dy dx all by itself. Cool. This is going to be a mess just because there's all kinds of nastiness going on. But before we do that, we have to get rid of the parentheses, which means I need to distribute this thing into here. Okay? All right. So this side over here is going to be, so this side's going to stay the same. This side right here is exactly the same thing coming down. Okay? When you distribute that in there, 1 over xy times y, what's going to cancel? The y's cancel. 1 over x plus 1 over xy times x. X's cancel. So it's 1 over y dy dx. How many dy dx's do you see here? Yeah, we got 2 of them. Now we have 3 of them. Crazies. There's 3 dy dx's. Copy. Paste. Great. This goes right in there. Okay? There's 3. There's 3 terms of dy dx. I'm going to get them all on one side. I'm going to get everything else on the other side. So, it doesn't matter what side you do. They're both correct. I'm going to leave all the non-dy dx crap over here on the left. Okay, it's only 2 terms. Root y, 1 over x. Everything else has a dy dx in it. So I'm going to put it on the right. We have the 1 over y. We're going to have to subtract off x over 2 root y. And we're going to have to add 1 over the absolute value of y times the square root of y squared minus 1. And they're all being multiplied by dy over dx, so you're going to factor it out. And I just did that all in one step. Is that okay? And my last step is to divide by those parentheses there. And again, because I can do this with this, digital amazingness that I have. When you divide by that, it just moves it all over here. And yes, this is a complex fraction. And yes, I told you to simplify these, but this is insane. I'm not going to simplify that nonsense. Okay? That's what dy dx equals. And on a test or something, we leave it just like that. There's no way we're ever going to work with something like this. Okay? This is just me making sure you know your ridiculous rules. Okay? It could be, but we're not going to simplify it. We're just going to let it be. Get dy dx by itself, let it be. Okay? Number 12. What's up, Minu? Okay. If we want the second derivative, we got to derive it, get dy dx by itself, just like we just did, and derive it again. So, we're going to derive 3xy with the product rule. We get 3y plus 3x dy over dx. And that equals 2x plus 2y dy over dx. Is that okay? I'm going to get, just like we did before, all the dy dx's on one side, all the non-dy dx's on a side. Again, it really doesn't matter what side you do it. I'm going to move all the dy dx stuff over to here. So you're going to have 3x dy dx minus 2y dy dx. And you're going to factor out a dy dx. And over here you're going to have this stuff left over. Okay? Then we're going to divide by 3x minus 2y. Okay? And then we want to find the second derivative of that, so we're going to derive this thing, which requires the quotient rule. Cool? So, we are going to, right over here, derive the left side, and dy over dx turns into d squared y over dx squared. That has got to equal, by the quotient rule, derive the numerator. That's going to be 2 minus 3 dy dx. Times the denominator, which is 3x minus 2y. Everybody with me still? Minus, the numerator stays the same. So 2x minus 3y. We're going to multiply that by the derivative of the denominator, which is 3 minus 2 dy over dx, all over the denominator squared. Is that okay? Good face.
X minus 2.
Huh? right here, because the derivative of 3x is 3. Okay? And the only thing to do, and I'm going to skip over in this video, and you can roll your eyes at me all you want, is to plug in what dy dx is. Okay? So, we really want to simplify that. We want to plug it in and simplify it, but this, again, is going to be, so when I gave this as a test, I just told the kids, just plug it in and don't worry about simplifying it. In reality, we want to simplify it, but this is just too much for this kind of question, okay? So you plug in what it is, simplify it if you can, but we're going to let it be. Sound good? Okay. Tangent lines. We want to find the tangent line when x is 0. First thing I'm going to do is plug in 0 and find out what y is. If you plug in 0, you get e to the 0 times cosine of 0, which is 1, and e to the 0 is 1, so this just equals 1. So right away, I know my tangent line is y minus 1 equals something, x minus 0. Okay? That slope comes from the derivative, so we're going to derive it. And y prime is going to be, by the product rule, the derivative of e to the sine x is e to the sine x times the derivative of sine x, which is cosine x. Okay? But there's already a cosine x there that I got to multiply by, so it's really going to be cosine squared x plus. What was that noise? Are we still recording? Yes. Okay. Plus, leave e to the sine x alone and derive cosine of x. And look how I'm going to put this in parentheses, everyone who's yelling at me about losing points. I'm not just going to put times and negative. I'm going to put parentheses, negative sine of x. There you go. Okay? And later on, man, have a good weekend. All you're going to do now, that's our derivative, is plug in 0. We want to know what's y prime of 0, because that's where we need the derivative. Y prime of 0 happens to be e to the 0, which is 1, times cosine of 0 squared, that's just 1, plus e to the 0, which is 1, times negative sine of 0, which is 0. So we did all that work to find out that the derivative just equals 1. So the tangent line is y minus 1 equals x minus 0. Okay? Okay. And last but not, I'm going to be late for my flu shot. If I get sick this summer, I'm going to miss it. God. The slope is 1. Yeah. Okay? So here, we were the tangent line when x is 1, but I don't know what y is, so I'm going to plug x in first to find y. When you plug in 1 for y, or x, you get y squared minus 5y equals 6. We got to solve this for y. I want to know what y is. Okay? That factors into y minus, nope, wait, maybe. Y minus 6, y plus 1, right? Well, that means that there's two y values when x is 1. We have 1 comma 6 and 1 comma negative 1. Cool. Did I ask about normal lines in this case too? Find tangent line, okay. So, we know one tangent line right here is going to be a y minus 6 equals something times x minus 1. And we know the other tangent line is going to be y plus 1 equals something, x minus 1. We just got to find that dy dx. Cool? So, we're going to derive it. To derive this ridiculous equation right here. X squared y squared minus 5xy equals 6. We got to do the product rule here. Okay? So that's going to be 2x y squared plus x squared times 2y dy dx. That's the derivative of the first piece there. Okay? Minus, we got to do the product rule in the second piece, so I'm going to put this in parentheses. The derivative of 5x, I'm going to lump 5x together, so it's 5x times y. So it's 5 times y plus 5x dy over dx. Okay. Now that's going to equal... Lily, come on now. What is that? Oh my God, Lily. Equals 0. I'm so clever. All right. I'm sorry. We gotta get dy dx by itself. When you do that, you should end up with this. All I'm doing is in my head, I'm moving over the 2xy squared. Okay, I'm in the way. 2xy squared. But we're also going to have a minus 5y, so I'm going to add that over to here. Then you're going to factor out dy dx, and what's going to be down here is 2x squared y minus 5x. You don't even need these parentheses down here. I don't know what I'm doing. Okay, and again, all I did was get dy dx, factored it out, divided. So all we got to do now to find the slope is plug in our points. So one point was 1, 6. Okay, so for 1, 6, the slope is going to be negative 2 times 1, that's just 1, times 6 squared. It's 36. Plus 5 times 6. That's 30. Divided by 2 times 1 squared, that's 1, or 2 times 1 is 2, times 6, minus 5 times 1, which is 5. Okay, that's negative 72 plus 30, which is negative 42, I think. Divided by 12 minus 5, which happens to be 7, which means the slope at 1, 6 is negative 6. So one tangent line is y minus 6 equals negative 6x minus 1. Okay? Then we got to plug in 1, negative 1. So let's go and do that. When you plug in 1, negative 1, we're going to get negative 2 times 1 times negative 1 squared. That's just negative 2 altogether. Okay? Plus 5 times negative 1, that's negative 5, over 2 times 1 squared times negative 1, it's negative 2, minus 5. So is that negative 7? Am I messing this up? You guys with me on this? If I messed up the arithmetic, I'm sorry. Whatever. But you're just plugging it in and simplifying it down. I'm rushing. We got 1, right? Yep. So the slope at that point is 1. Drop that in here. So your answer is really right here. These two lines.